So let's start our discussion with assignment 4. First, we are going to start our discussion with question number 5, 6 and 7, in which we have to find number of non-negative integer solutions of an equation. This we have discussed in detail in class. So first of all, we are going to understand the motivation of this thing, motivation of our how to derive the formula for number of integer solution of an equation. Actually, this is just like finding possible combination in which one object is repeated. So let's start. So the question is x plus y plus z plus w is equal to 15. So how many non-negative integer solutions are possible? So see, when we are going to find solutions, it means x plus y plus x, y, z, w, these are our four variables. They may take some values such that their summation sum is equal to 15, and these values should be non-negative. So non-negative means they could be either some positive number or they could be 0, but they cannot be negative. They cannot go, we cannot have like x is equal to -1 or -2, but they may have 0 value. Non-negative, 0 is a non-negative number. 0 is neutral, it's not positive, non-negative, so 0 is included. So we may have some value x is equal to 0 or y is equal to 0 or zw could be 0, and then or they may not be equal to 0, but their summation they should sum up to 15. In class we have discussed something like x1 plus x2 plus x3 is equal to 11, and so how many non-integer solutions are possible. So in class we also discussed one example, like if we have a basket of fruit, or we have we have 3 baskets of fruits in which we have apples, oranges and pears, and we want to select 4 fruits. We have basket of apple, we have basket of oranges, and we have basket of pears, and we want to select 4 fruits. It's our choice which fruit we are going to choose. So in how many ways we can choose 4 fruits? Actually, see, this problem of fruits is exactly the same as number of solution to equation. So it's just like we have, you can call apples as x, oranges as y, and pears as z. So it means we have to choose some number of apples, some number of oranges, and some number of pears. We cannot choose negative apples or negative oranges, but we can choose like 0 apple. We don't choose apples at all, or 0 pears. We don't choose pears at all. But combination of these 3 fruits, total fruits that we pick, that combination, that group, that set, it should be equal to 4. Size of the set should be equal to 4. It could be like we choose 2 apple, 1 orange and 1 pear, so 2 plus 1 plus 1 is equal to 4. So if we call apple as x, oranges as y, and pears as z, so x plus y plus z is equal to 4. So in our problem we have 4 types of variables. You can say we have one more fruit like banana, so x plus y plus z plus w, and we have to choose 15 fruits is equal to 15. So in how many ways we can do this? So let's look at with this simple example of 3 types of fruits, and we have to pick 4 fruits. So in how many ways we can choose this thing? So we can see if we list these down, so we can choose like 4 apples or 4 oranges or 4 pears or 3 apples, 1 orange, and going down till like 2 pears, 1 apple, 1 orange. So these are all possible ways to pick 4 fruits. In other words, these are all possible solutions to our equation of apple plus orange plus pears is equal to 4, or x plus y plus z is equal to 4. So these are all possible solutions, and we can count these 1 2 3 4 5 into 3, so total there are 15 possible solutions to this thing. So let's try to understand what could be the formula for this thing. We have listed this, but not all the time we can make a list, so it's better to have a formula for this. So instead of these baskets, so I write down like apples and oranges and pears. Fine. So just imagine these are my baskets, and this is one big box in which I have put dividers. So on one side it's apple, then there's a divider, then there are oranges, then there's a divider, then there are pears, and I have to pick total 4 fruits from apple, oranges and pears. So it could be like I can choose all 4 fruits from apple side. I've just made these fruits like we don't know whether it is orange or pear or apple. We just call it's our fruit. So I can choose all 4 fruits maybe from apple, or I can make some divisions. I can pick 2 fruits from apple and 2 fruits of type orange, or maybe I can take 1 apple and 2 oranges and 1 pear. So total there are 4 fruits. So you see I have these 4 fruits, and I'm actually just changing the position of dividers, these 2 dividers. Wherever I will put these dividers, so it means I have a different combination of fruits. So if I put these 2 dividers anywhere in between or on the sides, so I will get a combination of apples, oranges or pears. Like over here, both 2 dividers are on the side. So it means I have 4 apples, 0 oranges and 0 pears. Over here, so dividers have moved or fruits have moved. You can think in either direction. Either you are moving dividers or you are moving fruits in the dividers. So I have got 2 apples, 2 oranges and 0 pears. Another solution could be 1 apple, 2 oranges, 1 pear. Or one solution could be 0 apple, 1 orange and 1 pear. Or it could be like I select all 4 pears and 0 orange and 0 apple. So what's going on actually? You see these are you can call dividers and fruits. So how many dividers I have? 2 dividers. And how many fruits I have? 4 fruits that I have to pick. So these dividers, how many dividers I need? If I have 3 types of fruits, I need 2 dividers. If I add one more type of fruit, so I will need 3 dividers. If I'm left with just two type of fruits, apple and oranges, I don't have pears, then I need just 1 divider. So number of types of objects, types की बात हो रही है. Number of objects, we are not discussing number of objects. Number of objects की बात नहीं हो रही. Number of types of objects. How many types we have? We have 3 types. So if we have 3 types, so we need 1 less divider. Okay, so if we have 3 types, we need 2 dividers. So I can make an analogy of zeros and ones. These dividers I can represent it with 1, and these fruits that I'm going to select I can represent with 0. So I change the position of ones in between zeros, and I get different combinations of apples, oranges and pears. Or I can get different combinations of ones and zeros. Let's see. So when I move 2 fruits of orange, 2 fruits of apple, so it's 0 0, and then 1 is divider, and then 0 0, and then 1 is divider, and there is nothing, so it means I didn't choose any pear. So it depends where 0 occur. It means where fruits occur, from which type. So if 2 zeros are in the beginning, it means I'm choosing 2 objects of first type. Then there is a divider. Then I'm choosing 2 objects of second type, 2 zeros. Then there is a divider, 1. And then there are no zeros, so it means third type I didn't choose at all. Similarly, you can see if I move these fruits, so similarly I can move zeros between the ones. And if all 4 fruits are here, it means all 4 zeros are here. Okay, so what's going on? So how many ways we can put dividers between the fruits, or fruits between the dividers? In other words, in how many ways I can put 2 ones that I have got here? In how many ways I can put these 2 ones between zeros? In other words, I have to see all possible ways where I can put these 2 ones. In other words, how many bit strings I can have? This is a bit string, binary string of zeros and ones. How many bit strings I may get with 2 ones and 4 zeros? Obviously, if the length is 6, there are 2 ones, so there are 4 zeros. So how many bit strings of length 6 with exactly 2 ones I get? So this problem we have already done in first questions of this assignment. So if we have length n and there are r ones, so how many bit strings I can have? Answer is n, choose r. So if I have length 6, length of binary string is 6, and there are exactly 2 ones, so how many binary strings I can get? 6, choose 2. We can say 2 ones or we can say 4 zeros, so it's 6, choose 4. So 6 choose 2 and 6 choose 4 is same. We have already know from the symmetry of binomial coefficient. So for this, answer is 6 choose 4. If we solve it, we will get answer 15. So 6, how we get 6? So it's number of types, which are 3 types of roots. So how many dividers we need? Number of types minus 1. So 3 minus 1. So that many dividers or that many ones I have. And how many objects I am going to choose? These are 4 fruits or 4 zeros I am going to have. So 3 minus 1 plus 4. The length of binary string becomes 3 minus 1 plus 4. Number of types minus 1. These many ones I get, or these many dividers I get. 3 minus 1 dividers I get, which is 2 here. Plus 4. So these are zeros, are these fruits that I get. So binary string length is 3 minus 1 plus 4, which is 6. So in which I have exactly 4 zeros or exactly 2 ones is same thing. So in general, I can write down the formula. If I have n types, the number of dividers are n minus 1, or number of ones are n minus 1, and I have to choose r objects, or I have to choose r zeros. So binary string becomes n minus 1, these are the ones, and r zeros, so n minus 1 plus r. That is the length of binary string. So how many possible binary strings are there? It is like we keep on changing position of ones and zeros between them. So how many possible bit strings I can get? So n minus 1 plus r, choose r. So length of binary string is n minus 1 plus r, and I have to choose r zeros. So fine. So I can write down this apple, orange and pear now in equation form. How to write it in equation form? So instead of apple, I call these as x1, and oranges I call them x2, and pears I call them x3. So just like before I had apple, orange, pear, now I have x1, x2, x3. And how many fruits I have to pick? I have to pick 4 fruits. So it means x1 plus x2 plus x3, this should be equal to 4. And how many solutions now I have? Number of dividers n minus 1, so 3 minus 1 is 2. And how many fruits I have to pick? 4. So length of binary string is going to be 3 minus 1 plus 4. So 3 minus 1, 2 plus 4, 6. Length of binary string is 6, and I have to choose exactly 4 zeros. In how many ways I can do this is 6, choose 4. So the answer is 3 minus 1 plus 4, choose 4, 6 choose 4 is equal to 15. Okay, I hope you have got this example, and if you have got it, then we can easily move to our original question. In our original question, we have x plus y plus z plus w is equal to 15. So types of objects we have got is 4. And how many objects we have to choose now is 15. So it means new equation should be x plus y plus z plus w is equal to 15. Now n is equal to 4, and r, the number of objects that we have to choose, is 15. So how many bit strings of length n minus 1 plus r with exactly r, which is 15 here, zeros are possible? So now you can do this question. So let's move to part B. So now we have given restrictions. So equation is like we have now 5 types, x1, x2, x3, x4, x5 is equal to 25, such that x1 should be at least 1. Greater than or equal to 1 means it is at least 1. at least x1, value of x1 should be at least 1, and it could be more than that. X2 should be at least 5. X2 is greater than or equal to 5. X2 should be at least 5, and X3 is greater than or equal to 15, means X3 is at least 15. So again we can try to see the fruits example first to understand, and then we can solve this example easily. So let's start reformulate the fruit example. X1, X2, X3. We have apples, oranges, and pears. First we try to solve this problem, and then we'll come back to our original problem. So we have to pick 4 fruits from apples, oranges, and pears, with the restriction that at least 1 apple should be there, and at least 1 orange should be there, and at least 1 pear should be there. So we have got 3 fruits, 1 apple, 1 orange, and 1 pear, and our choice is left with only 1 fruit, because at least we should have 1 apple. We cannot have like 0 apple. At least there should be 1 apple, at least there should be 1 orange, at least there should be 1 pear. In how many ways we can do this? So if I write in a equation form, it's like apples should be at least 1, means apples is greater than or equal to 1, oranges is greater than or equal to 1, pears are greater than or equal to 1. So greater than or equal to 1 means at least I need 1 apple, so I separate 1 apple here. At least I need 1 orange, so I separate 1 orange here. At least 1 pear I need, I mean I have no choice, at least I should have 1 pear, so I put 1 pear aside. So how many fruits I have already got? I've got 3 fruits, 1 apple, 1 orange, 1 fruit. In total, how many fruits I am supposed to pick up? I should pick up 4 fruits, and I have already got 3 fruits, so my choice is left with only 1. So it means 1, I can either choose apple, or I can choose orange, or I can choose them as pear. So I have 3 possible solutions. So I can either choose as apple, or as orange, or as the one fruit of my choice as pear. So for 4th fruit I have 3 choices. That's fine. How to do it in equation form? So you can see over here I am getting a binary string of length 3. 2 are my dividers. For these 3 types I need 2 dividers, and 1 is 1 fruit that I have to pick. So it means I am going to have n, which is 3, so n minus 1 is 2 dividers, plus r is 1. So 2 plus 1, which is 3, choose 1. I can only choose 1 fruit, so 3 choose 1, which is equal to 3. So possible solutions are n minus 1 plus r, choose r. So 3 minus 1 plus 1, choose 1. 3 choose 1 is equal to 3. I have 3 possible solutions. That's fine. So if in our equation, in the problem, now I hope you can easily get it. In the problem we have got is n is equal to 5. So we have got number of objects, number of variables is equal to 5. x1, x2, x3, x4 is equal to 5. So n is equal to 5 types of variables, and how much objects I have to take it in any case. There is x1 should be greater than equal to 1. So I have no choice. I have to choose 1x1. Similarly, I have to choose 5 of x2. So 1 of x1, 5 of x2. So 6 objects I have separated, and then I need 15 of x3. So 1 plus 5 plus 15. 21 objects I have to separate it. I have no choice. I have to carry them in any case. So these are not in my choice. Just like in the previous example, I had to choose 1 apple, 1 orange, 1 pear. Now I have to choose 1x1, 5x2, and 15x3. Compulsory, because on top of these numbers I have choices. For these numbers I don't have choices. I have to carry these in my basket. On top of these, if I get like one more x1, so that's fine. I will get 1 plus 1 2x1, and that my problem allows me. Or if I can get one more x2, so 5 I already have, I will get one more x2, so I will get 6x2. Or for example, if I get 2x3 more, so 15 I already have, I get 2 more x3, so I will get 17x3, and so on. So it means 1 plus 5 plus 15, which is 21. These 21 objects I have separated, and now my new equation becomes x1 plus x2 plus x3 plus x4 is equal to 25 minus 21. 21 objects I have already separated. Total I have to choose 25. So now I can choose only 4 more objects from either of these types, either from x1 or x2 or x3 or x4 or x5. So this is my new equation. x1, x2, x3, x4, x5, their summation is equal to 4. So how many possible solutions I have? So n is equal to 5, r is equal to 4. I have formula n minus 1 plus r, choose r. So I can find number of possible solution for this problem. So next move to part C. So now things have become easy. X plus y plus z plus w is equal to 15, such that w is equal to 5 and z is greater than equal to 5. Again, we go back to our fruit example. Apples are x1, oranges are x2, pears are x3. We have to pick 4 fruits with the condition that apples should be equal to 1. It should be equal to 1, exactly 1. And oranges should be greater than equal to 1. For oranges we don't have, for apples we don't have any choice. Apple, I have to pick one and only one. Apples is equal to 1. It's equality. I cannot take apple less than 1. I cannot take apple more than 1. So it means we have found the exact value of apple. So from our equation, x1 plus x2 plus x3 is equal to 4. Apple value is known, so x1 is equal to 1. So we are left with the equation x2 plus x3 is equal to 4 minus apples, 4 minus 1. So x2 plus x3 is equal to 3. But oranges should be greater than equal to 1. We separate one orange that we need, but we can have more than one. We may have just one orange, or we can have more than one orange. So orange we separate one, so but still we can pick more oranges. So oranges we cannot exclude from our equation. So new equation will become x2 plus x3 is equal to 2. So we have to pick 2 fruits from oranges and pears. So over here now, because apples are no more in equation, so we don't put apple over here. So apples divider and 1 is no more needed. So our equation just become oranges and pears, and we have to pick 2 fruits. Either we can pick both oranges or both pears, or 1 orange and 1 pear. So there are 3 possible solutions. In other words, x2 plus x3 is equal to 2. So how many solutions are possible? N, value of n become now 2. So n minus 1 is 2 minus 1, plus r, value of r is 2. So 2 minus 1 plus 2, choose r, choose 2. So 3 choose 2 is equal to 3. So I hope now from our original problem we can solve. We have x plus y plus z plus w is equal to 15, with w is equal to 5. So means value of w we have already found it out. So we can just plug in the value of w. We can just plug in the value of w in this equation. So w is equal to 5. So this will become x plus y plus z is equal to 15 minus 5, 10. X plus y plus z is equal to 10. And then we have to solve for z is greater than equal to 5. For this thing we have to solve it. Okay, so let's see. So equation in the problem, w is equal to 5 is fixed, we keep it separate, and z is greater than equal to 5, so we have to keep z is equal to 5 separate, and on top of this we can choose anything. So new equation becomes x plus y plus z is equal to 15 minus 5 minus 5, 5 of w and 5 of z. So x plus y plus z is equal to 5, and then we have to solve using n minus 1 plus r, choose r. Please keep in mind, when we have equality like over here, w is equal to 5, so it means w is excluded from our equation. W is excluded altogether from our equation. When we have inequality, z is greater than equal to 5, means we have to choose objects at least 5. So 5 we keep it on one side, and still we can choose more objects. So be careful about this equality and inequality. When equality, it means we have got the solution, so we separate it. When we have got inequality, it means still we can have more objects of this type. So be careful for this thing. So thank you very much for this question. So let's go with problem number 6. In how many ways can you distribute n pennies to k children if each child is supposed to get at least 5 coins, 5 pennies? We solve this problem in class in a different way, but we can solve this just using this solving equation way. First of all, consider any child may get any number of coins, even they can get 0 coins. So first let's try to solve this problem, and after that we will come back to the problem of 5 pennies. So we will come back to at least 5 penny problem later. First we try to solve this thing that they may get any number of coins, even 0 coins. Okay, so suppose we have n is equal to 100. We have 100 coins. Okay, and we have number of children, k is equal to 4, Alice, Bob, Carl and Dion. We have A, B, C, D, 4 kids. So we have 100 pennies and we want to distribute these to 4 kids, A, B, C, D. So all kids have got some number of coins, and if we sum up coins with all children, so we get this equation: A plus B plus C plus D is equal to 100. Number of coins with Alice, number of coins with Bob, number of coins with Carl, and number of coins with Dion. All together, when we sum them up, the sum is equal to 100. So we have 100 coins and we have to distribute among 4 kids. So it means after distribution, when we sum up their coins, these should be equal to 100. Voila. So we have got an equation: A plus B plus C plus D is equal to 100. So how many possible solutions are there? Like in how many ways value of A can be changed, value of B can be changed, value of C can be changed, value of D can be changed. These values are the number of coins with each of these children. हर एक बच्चे के पास कितने coins हैं? A, B, C, D is telling us this thing, and this number should be equal to 100. So we have 4 variables and their sum should be equal to 100, and any child may get coins equal to 0 as well. So it's like non-negative integer solutions. So this we have done number of times from our previous discussion. So n minus 1 plus r, choose r. So over here just be careful what is the value of n and k. So k is number of types. We have 4 types of kids, so k is 4. So 4 minus 1 is 3, and we have to choose 100 coins that we distribute among them. So 3 plus 100, 103, choose 100. So in that many ways we can distribute these coins among k children. This we have already done. So now in our question, what does it say? Our question says each child could get should get at least 5 coins. Every child should get at least 5 coins. It means Alice should get at least 5 coins. Bob should be, his number of coins should be greater than or equal to 5. Carl coins should be greater than or equal to 5. Diane coins should be greater than or equal to 5. Each and everyone should have at least 5 coins. So this is exactly the same problem that we have done before. So we separate, first of all, it's just like give 5 coins to each and every child and then get the new equation. What is the new equation? We try to solve that equation. So if we give each child 5 5 5 coins, so we are left with 100 minus 5 minus 5 minus 5 minus 5. So these we already give to all children. So each child has get at least 5 coins. On top of that, they may get any number of coins. So if we get 5 coins, if we give 5 coins to each child, then we are left with 80 coins. And our new equation is A plus B plus C plus D is equal to 80. And from this equation, we have to see how many possible solutions are there. We have 1, 2, 3, 4 types. So 4 minus 1 is equal to 3. So we have to choose 80 coins that we are going to distribute among these 4 kids. So we have like for the 4 kids we have 3 dividers and we have to put 80 coins between those dividers, just like in previous example we did, previous exercise. So it's going to be 4 minus 1 plus 80, choose 80. 83, choose 80 possible solutions. So now each child has already got 5 coins already. So on top of that, how many coins they are going to get? So whatever they will get, it is more than 5 coins, obviously no. So you can we have already found out how many possible solutions are there. So and that was when we have n is equal to 100 and k is equal to 4. If we have we can now generalize our solution that we have n number of coins. Now n is not 100, n could be any number, and we have k children. K could be any number. Each child get at least 5 coins. So it means among k children, to each child we give 5 coins in the beginning. So how many coins we have given? 5 times k. So from n we have given 5k coins already to k children. So we will be left with n minus 5k coins. So after giving 5k coins to every child, we will be left with n minus 5k, and our equation is x1 plus x2 plus x3 plus xk. So these are k children. So sum of k children coins after giving 5 coins to each and every child, we have got x1 plus x2 plus x3 plus xk is equal to n minus 5k. So how many solutions are possible? So how many variables we have? We have k variables. And how many objects we have got? How many coins we have got? N minus 5k. That we have to distribute among k children. So this we have done now many times. The formula, remember that n minus 1 plus r, choose r. N is type, in the formula n is type of variables. Over here we have type of variables is equal to k. So it becomes k minus 1 plus r. The value of r over here is n minus 5k. So k minus 1 plus n minus 5k. Choose this r, so n minus 5k. So you can now solve this. You can solve this question, final answer by yourself. It's it's easy, it's obvious now. Yeah, so problem number 6 is over. Thank you. Let's start with problem number 7. So again, it is very much same question as fruits question or solving an equation. So in a toy shop we have 15 airplanes, 15 buses, 15 trains and 20 bikes we have got. So these many are in the stock. Okay, so how many ways are there for a person to take 15 toys? He has to pick 15 toys if all airplanes are same. There are only one type of airplanes and there are 15 airplanes, so he can pick all 15 airplanes altogether as 15 toys. And all buses are identical. I mean, you cannot distinguish one bus from other. So if we pick one bus and again one bus, so they are like same bus. So it's just like a combination with repetition. All trains are identical and all bikes are identical. So it means we can write down equation for this problem. So let's call x1 as airplanes, call buses as x2, trains as x3, bikes as x4, and we have to choose total 15 toys. So it means we have got an equation. Airplanes plus buses plus trains plus bikes is equal to 15. x1 plus x2 plus x3 plus x4 is equal to 15. How many solutions are possible? We have got 4 types of toys. So n minus 1, 4 minus 1 plus r. So how many toys we have to pick? 15 toys. So we have got 4 minus 1 plus 15, choose 15. That is some obvious thing, not so hard. B part is quite straightforward. All toys are distinct. All airplanes are distinct. All buses are distinct. All trains are distinct, and all bikes are distinct. Distinct means one airplane is different from the other one. One is different from the second is different from the third is different from fourth, and so on. All 15 airplanes are different from each other. All 15 buses are different from each other. All 17 trains are different from each other. Each and every toy is distinct. So that means we have all different toys. Not one is same as the other one. All distinct objects. There's no repetition. So it means we can just use our simple combination formula. So how many toys we have got now? 15 airplanes plus 15 buses plus 17 trains plus 20 bikes. And how many toys we have to choose? Out of these we have to choose 15 toys. So we know NCR formula, we can use it and choose R. So total available toys which we have counted here, and we have to choose 15 toys, so we can solve this thing. That was simple. Part C is interesting. So how many ways are there for a person to take 25 toys if all airplanes are, like in the first part case, identical, or buses are identical, trains are identical, and all bikes are identical? Now we have to choose 25 toys. But how many airplanes we have? We have got 15 airplanes. It means we cannot choose more than 15 airplanes. We cannot choose more than 15 buses. We cannot choose more than 17 trains. And we cannot choose more than 20 bikes. But altogether, x1 plus x2 plus x3 plus x4, this should be equal to 25. So now we cannot use that formula straight away of n minus 1 plus r, choose r. We will get some illegal solution, because that formula holds when we may have like x1 is equal to 25 and x2, x3, x4 is equal to 0 here. That is one possible solution. So in that case, x1 can take any value from 0 to 25. x2 can take any value from 0 to 25. x3 can take any value from 0 to 25. x4 may take any value from 0 to 25. But in this case, they cannot take any value, because we are restricted with the number of toys. We have 15 airplanes, 15 buses, 17 trains, and 20 bikes. So x1 can take maximum value up to 15. Buses can take maximum value up to 15. Trains can take maximum value up to 17. And bikes can take maximum values up to 20. So how to solve it? So if we just solve this equation, we will get a number of illegal solutions, like x1, value of x1 may go more than 15 and so on. So it means what we have to do is, as usual we often do, is find the legal solution. We find total solutions and we subtract illegal solutions from the total solutions. So we'll get legal solution, allowed solution, valid solution. So first of all, we calculate total solutions. That is easy. So x1 plus x2 plus x3 is equal to 4. So we can find n minus 1 plus r, choose r. So we get like 28, choose 25 as total solutions. These total solutions also include those illegal solutions. So we need to find illegal solutions and then simply subtract those illegal solutions. So what are those illegal solutions? Illegal solutions are when we have x1 is greater than 16, or x2 is greater than 16, or x3 is greater than equal to 18, or x4 is greater than equal to 21. These all come from these restrictions, because we have x1 maximum 15. We cannot have more than 16, more than 15. If we get 16, so that is an illegal choice. If we have some buses, a solution in which number of buses comes to be 16, so it means it's not a valid solution, because we have maximum buses equal to 15. If we got trains x3 greater than equal to 18, it means it's not a valid solution. We have maximum of 17 trains. Similarly, we have got maximum 20 bikes. So if we get in some solution value of x4 greater than 20, so that is not a valid solution. That is an illegal solution. So we need to find number of illegal solution and we will subtract it from our total solutions. So how to find a number of illegal solution? We have to avoid overcounting, of course. So this is just like principle of inclusion exclusion. So we solve for illegal solutions. So first of all, we solve for when x1 is greater than equal to 16. So we have to solve each and every case, and let's call it a1. So when x1 is greater than equal to 16, we have solved it many times. So we are just taking one condition. We are just taking only one condition. Only one condition we are looking at. So x1 is equal to greater than 16. So we have, it means 16 x1 we separated. So from 25 we separate 16 x1. So now our new equation will be x1 plus x2 plus x3 plus x4 is equal to 9. So our equation will be x1 plus x2 plus x3 plus x4 is equal to 25 minus 16 is equal to 9. So we solve for this thing. X1 plus x2 plus x3 plus x4 is equal to 9. So this will be those solutions in which x1 is greater than equal to 16. Next we solve for when x2 is greater than equal to 16. We solve for this thing. Again, equation will be just like same. We will get number of solutions, and then after that we will solve it for x3 is greater than equal to 18. Again we make some equation like this, 25 minus 18, which will be 7. So x1 plus x2 plus x3 plus x4 is equal to 7. Then we will solve for x4 is greater than equal to 21. So our new equation will be x1 plus x2 plus x3 plus x4 is equal to 25 minus 21 is equal to 4, and we solve for this thing. So we'll get 4 solutions, a1, a2, a3, a4. But we have to be careful. Do we do some over counting? Because in principle of inclusion exclusion, we have to subtract the intersection. So do we need to calculate the intersections like a1 intersection a2, etc.? This I mean, just looking at this condition, the answer is obvious. So I mean, you can answer by yourself. do we need to calculate the intersections or not. So we find illegal solutions like this. So we sum all these a1, a2, a3, a4 to find illegal solution. And for legal solutions, from total solution we minus subtract the illegal solutions. Total solutions minus illegal solutions, this will give us the legal possible valid solutions. So that summarize our problem number 7. So thank you very much for your listening and patience.